There is a star 390 light-years from Earth that contains elements which should not exist. Not rare elements, not exotic elements. Elements that decay into nothing within decades. Radioactive isotopes with half-lives so catastrophically short that every gram of them should have been gone billions of years before our solar system was even dust. And yet, there they are. Burning. Present. Impossible. That star has a name, and once you learn what it contains, you will never look at the night sky the same way. But before we get there, before we unravel that particular impossibility, we need to talk about a deeper problem. Because that star is not alone. Across the galaxy, scattered through globular clusters 10 billion years old, hidden inside the cooler outer shells of red supergiants, pulsing in X-ray wavelengths from 45,000 light-years away, there are stars that simply refuse to behave, stars that defy the models, stars that have aged backwards, that harbour dead stellar cores in their hearts, that flare with energies capable of ionising our atmosphere from across the Milky Way, that grow younger as everything around them grows old. Stellar physics is one of the most rigorously tested scientific frameworks ever constructed. We can predict with extraordinary precision how stars are born, how they live, how long they last, and how they die. The Hertzsprung-Russell diagram, that elegant scatterplot of temperature against luminosity, is not merely a chart, it is a periodic table for stellar existence. It tells us where a star belongs. These stars are not where they belong. To understand why certain stars are rule breakers, you first have to understand the rules themselves. And those rules, for all their mathematical elegance, were assembled slowly, painstakingly, over more than a century of dead ends and unexpected breakthroughs, by scientists working with instruments we would now consider primitive, puzzling over objects so distant and so ancient that comprehending them at all requires a kind of sustained imaginative leap. Most of us never attempt. The foundations were laid in the mid-19th century, when astronomers discovered they could do something that seemed, at first, almost philosophically absurd. They could determine the chemical composition of the sun without ever visiting it. The key was spectroscopy. When starlight passes through a prism or a diffraction grating, it spreads into a rainbow spectrum, but embedded in that spectrum are dark lines, precise, fingerprint-specific wavelengths where particular elements have absorbed the light. Sodium leaves its mark, hydrogen leaves its mark, iron, calcium, helium, all of them leave marks. Every element in the universe has a signature as unique and identifiable as a human face, and the sun's spectrum carries thousands of those signatures simultaneously, like a passenger list written in light. This was the first great revelation. The cosmos is not made of alien, unknowable substances. The stars are built from the same atoms that make up the ground beneath your feet. The universe, at its core, is chemically continuous. That insight took decades to fully absorb, and even now, sitting with it quietly, it retains a quality that I find genuinely extraordinary. The iron in your blood was forged in the death of stars, not metaphorically, not approximately. Literally, the precise iron atoms in your hemoglobin were assembled in the nuclear cores of massive stars that exploded billions of years before our sun existed. By the early 20th century, two astronomers working independently, Ejnar Hertzsprung in Denmark and Henry Norris Russell in America, had begun plotting stars on a two-axis chart, luminosity against surface temperature. What they found was not a random scatter, the stars clustered into patterns. The vast majority fell along a single diagonal band running from hot bright at the upper left to cool dim at the lower right. They called it the main sequence, and it was not decorative, it was a physical law made visible. A star's position on the main sequence is determined almost entirely by one variable, its mass. Massive stars burn hotter and brighter, low-mass stars burn cooler and dimmer. The main sequence is, in essence, the universe's rule that says, given a mass, here is where you live. There were outliers, of course. Giant stars sat above the main sequence evolved and bloated, their outer layers swollen to hundreds of times solar radius as they aged. White dwarfs sat below it, dense and cooling the dim embers of dead stellar cores. These were accounted for. They were the expected endpoints of stellar evolution, like knowing that a person who was once a child will eventually become elderly. The timeline went like this. A gas cloud collapses under its own gravity. It heats up. When the core temperature reaches approximately 10 million degrees Celsius, hydrogen fusion ignites. The star arrives on the main sequence. For most of its life, which, depending on mass, could be anywhere from a few million years for a massive star to trillions of years for a red dwarf, it burns hydrogen into helium. It is stable, predictable, and well-behaved. Eventually, the hydrogen in the core is exhausted. The core contracts, heats up further, and the outer layers expand. The star becomes a red giant. For lower mass stars, this ends in the gentle expulsion of a planetary nebula, and the exposed remnant becomes a white dwarf. For massive stars, the core collapse is catastrophic and terminates in a supernova. This is the fundamental grammar of stellar existence. It is tested, robust, and applies across the entire observable universe. Every star we have examined in detail has confirmed it. The main sequence is not merely a statistical trend, it is a physical necessity, a consequence of the laws of gravity, thermodynamics, and nuclear physics operating together. And then there are the stars that simply do not agree. These are not minor deviations. They are not rounding errors. They are stars that appear in places in the Hertzsprung-Russell diagram where no star should survive. Stars that contain elements so unstable they should have ceased to exist before recorded human civilization began. Stars that pulsate with energies capable of being detected across half the galaxy, and whose magnetic fields are so powerful that they would, at a distance of 1,000 kilometers, distort the electron orbitals in your very atoms. Stars that look, from a distance, like one thing and are, on closer inspection, a completely different thing nested inside. The rules exist. These stars simply chose not to follow them, which raises three questions that will haunt us throughout this entire story. How do they form? How do they survive? And what, if anything, do they tell us about the gaps in our understanding that we have not yet had the courage to confront? In 1953, an astronomer named Alan Sandage was doing something that sounds, on paper, entirely routine. He was measuring the brightness and colour of stars in the globular cluster Messier 3, a gravitationally bound ball of approximately 500,000 stars sitting some 33,900 light-years from Earth in the constellation Canes Venatici. Messier 3 is what astronomers call an old cluster. Its stars formed approximately 11.4 billion years ago, meaning every star in it has been evolving for more than 80% of the age of the observable universe. In a cluster that old, the chemistry is settled and the rules are firm. What Sandage found stopped him cold. There were stars in Messier 3 that were sitting on the upper main sequence. Hot, bright blue stars, where no star in an 4 billion year old cluster had any business being. In a cluster that old, every star massive enough to burn hot and blue should have exhausted its hydrogen fuel billions of years earlier, and either exploded or evolved off the main sequence entirely. The hot blue stars should be gone. The upper main sequence should be empty. And yet here were these stars, sitting in their places, burning with the youthful fires of much younger objects, as if they had simply decided that the 11 billion years everyone else had experienced had not applied to them. Sandage named them Blue Stragglers, stars that had somehow lagged behind in the aging process, stragglers in the relentless march of stellar time. The name has stuck for 7 decades. The problem has not been solved in that same interval, not entirely, though we have come to understand the outlines of what is happening. And the outlines are, I would argue, one of the more disturbing stories in all of stellar astrophysics, because what these stars represent is not a young star at all. It is the product of a theft. Let us think carefully about what a globular cluster is. Messier 3's 500,000 stars were all born from the same collapsing gas cloud at approximately the same time. They are, cosmically speaking, siblings. They have aged together in the same chemical environment, under the same gravitational rules. When you plot all the stars in a globular cluster on a Hertzsprung-Russell diagram, you get a characteristic shape, a main sequence that is truncated at the top The turn-off point, because every star above a certain mass has already evolved off and become a giant or died. The exact position of the turn-off point is how we determine the cluster's age. It is in effect a clock. In Messier 3, stars with masses greater than about 0.8 solar masses have already left the main sequence, which means any star currently burning on the upper main sequence of that cluster must, by definition, be either younger than 11 billion years, or somehow more massive than it should be. Neither of those options is supposed to be possible in a closed stellar system. For years after Sandage's discovery, astronomers cycled through proposed explanations and found each one wanting in critical ways. The simplest suggestion, that blue stragglers were simply stars that had formed later, from leftover gas, was dismissed when surveys repeatedly failed to find the residual material necessary for such late formation. Stars in globular clusters don't form late. The gas was consumed or expelled in the original formation event. The cluster is not a stellar nursery, it is a stellar museum. The second proposal was more disturbing, and it turned out to contain a grain of truth. What if two stars, two aging siblings from the original cluster, had collided? Not in the chaotic, random scatter sense of two cars on a motorway, but in the long gravitational dance sense of stars in a dense stellar core whose orbits slowly decay toward one another and merge. If two stars merge, their combined mass exceeds either progenitor. A star that had been sitting on the lower main sequence, a dim low-mass object, could suddenly find itself with twice the fuel it previously possessed, and twice the gravitational compression driving its core temperature. In principle, it would look young again. It would burn hot and blue. It would sit exactly where a young massive star should sit. This is the stellar collision pathway, and in the densely crowded cores of globular clusters, where stellar densities can reach 10,000 stars per cubic light-year, it is not implausible. The crowding is extraordinary, and over billions of years, close encounters are not rare. The collisional model predicts that blue stragglers should be most numerous in the dense, collision-prone cores of clusters, and for some clusters, that prediction is confirmed. In Messier 30, a compact globular with a collapsed, ultra-dense core, blue stragglers are heavily concentrated toward the centre, consistent with having been formed by collisional mergers. But Messier 3 is not Messier 30, and when astronomers began systematically surveying blue straggler populations across many different clusters, a more complicated picture emerged. In clusters like NGC 188, an open cluster roughly 800 light-years from Earth in the constellation Cepheus, with an age of about 7 billion years, the blue stragglers were not in the dense core. They were spread through the cluster more broadly, and more critically, when Robert Mathieu and Aaron Geller at the University of Wisconsin-Madison conducted a meticulous 20-year survey of NGC 188. Using the Wyand telescope in Tucson, Arizona, they found something that the collisional model could not explain. 16 of the 21 known blue stragglers in NGC 188, that is, 76%, a figure that cannot be attributed to coincidence, were in binary systems. They were not single, rejuvenated collision products, but stars that each had a companion. And that companion was, in virtually every case they could confirm, a white dwarf. Think about what that means. A white dwarf is the cooling remnant of a star that has already lived and died. A stellar corpse. For a blue straggler in NGC 188 to have a white dwarf companion, the white dwarf must once have been the more massive, faster evolving member of a binary pair. It would have grown into a red giant first, and in doing so, it would have done what giant stars in close binaries frequently do. Would have expanded until its outer layers drifted across the gravitational boundary between the two stars, the Roche lobe, and began flowing onto its companion. Mass transfer. The companion star, originally a normal low-mass object, gorged on the fuel flowing from its dying neighbour. It grew more massive, its core temperature increased, its position on the Hertzsprung-Russell diagram shifted upward and to the left toward the hot blue region. The donor star, stripped of its outer layers, shrank and eventually became what it now is. A white dwarf companion, orbiting the engorged, apparently youthful star it has unknowingly created. Astronomers call this stellar vampirism, and the term is not merely colourful, it carries precise physical meaning. One star, through no malice of its own, drains the life force, the hydrogen fuel, of its companion, and in doing so, grants that companion a grotesque simulacrum of youth. The Blue Straggler is not a young star. It is an old star wearing a stolen skin, a false youth maintained by resources that were never its own. The orbital periods measured by Geller and Mathieu ranged from roughly 100 to more than 3,000 days, with a significant concentration around 1,000-day periods. Those long periods imply that the mass transfer happened across a considerable distance, through a mechanism more gradual and complete than a violent stellar collision. The white dwarf companions average about 0, 53 solar masses, precisely the mass expected for a star that originally had about 1.5 solar masses, and donated the remainder to its now blue companion. The numbers mesh with uncanny precision, and yet the story is not entirely resolved. The collisional pathway still seems necessary to explain blue stragglers in the densest, most collision-prone clusters, so there may be two separate mechanisms producing the same observable outcome. Two entirely different crimes, so to speak, leaving the same shaped body. In the Museum of Dead Stars, there is more than one way to fake a youth you never earned. There are approximately 300 globular clusters in the Milky Way alone. A conservative estimate suggests that blue straggler stars account for roughly 0.1% of the total stellar population in any given cluster, which sounds small until you remember that some clusters contain millions of stars and that across the entire observable universe there are hundreds of billions of galaxies, each with their own cluster populations. There are, conservatively, billions of these vampire stars burning in our universe right now, each one a stolen fire burning in a stolen body. I find it quietly extraordinary that this discovery originated with a single astronomer performing a routine photometric survey 7 decades ago, armed with a photographic plate and a measuring engine, noticing that something did not belong where it was. Science has rarely announced its most profound insights with fanfare. They arrive as anomalies, as numbers that don't line up, as a young-looking star in a very old field. The question Sandage's discovery opened: how can a star be young in a place where there is no youth left? Would take decades and multiple generations of researchers to partially answer. And even now, the blue straggler population of some clusters resists clean explanation. Not every binary fraction matches the mass transfer model perfectly. Not every blue straggler has a white dwarf companion. In some clusters, the numbers and the distributions suggest a third pathway, involving hierarchical triple star systems, in which a third, outer star gravitationally destabilizes the inner binary, driving the two inner components toward merger, which means that in the cosmos, there appear to be at least 3 separate mechanisms for producing a star that looks younger than it should be. 3 different crimes, 3 different methods, the same victim. The rule that says old stars don't burn hot and blue, but blue stragglers, for all their strangeness, are still made of normal stellar material. They are still fusion-powered, hydrogen-burning objects, in roughly the right places in the sky, doing roughly stellar things. They are cheating the aging process, but they are doing it with tools that, on some level, we understand. The next category of stellar rule breaker is doing something far more fundamental, far more difficult to explain. Something that doesn't merely bend the rules of stellar aging, but appears to violate the deepest principles of stellar chemistry. Its story begins in Australia in 1961, with a spectrum that made no sense whatsoever. In 1961, a Polish-Australian astronomer named Antoni Przybylski was working at the Mount Stromlo and Siding Spring observatories in New South Wales, analysing the spectral lines of a star catalogued as HD 10165, located in the southern constellation of Centaurus, at a distance of approximately 390 light-years from Earth. The star appeared, in broad terms, unremarkable, a faint point of light in the southern sky, slightly dimmer than what the naked eye can comfortably detect. What Przybylski found in its spectrum was, to put it plainly, one of the most confounding results in the history of observational astrophysics. Normal stars, when their spectra are analysed, show the spectral fingerprints expected for their chemical composition, primarily hydrogen and helium, with smaller amounts of heavier elements like iron, calcium, and sodium distributed according to the standard predictions of solar nucleosynthesis. A star like our Sun, when its spectrum is decomposed, gives you a very specific distribution of elemental abundances. Even chemically peculiar stars, the so-called API stars, show anomalous enhancements of certain heavy elements due to the slow gravitational separation and radiative levitation of atoms in magnetically stabilized atmospheres, produce spectra that are unusual but interpretable. HD 1165 was different. Przybylski found spectral lines he could not identify, lines that did not match hydrogen, not helium, not iron, not any of the common elements he expected. In a paper published in the journal Nature in 1961, he noted that the star had what he called a peculiar spectrum of unknown type. Over the subsequent decades, as spectroscopic instruments became more refined, and as the databases of atomic spectral lines grew more comprehensive, astronomers began to identify some of those mysterious features. The elements they matched were not, in any ordinary sense of the word, believable. Przybylski's star, as it became known, shows spectral evidence for concentrations of neodymium, praseodymium, cerium, terbium, holmium, erbium, and at least 14 other rare earth elements at abundances elevated thousands of times above what standard stellar physics would predict. These are elements from the lanthanide and actinide series of the periodic table, the heavy elements near the bottom, with high atomic numbers, the products of slow neutron capture in the interiors of dying stars. Their presence in any star at elevated concentrations is unusual. Their presence in these quantities is extraordinary, but the truly anomalous discovery came later, as spectroscopic analysis was pushed to ever greater precision. Buried in the spectrum of HD 11065, astronomers began to find absorption lines that matched not just unusual stable elements, but radioactive ones. Technetium was identified, an element with no stable isotopes at all, whose longest-lived naturally occurring isotope has a half-life of approximately 4.2 million years. In a star 11 billion years old, every atom of technetium that was present at its birth should have decayed into ruthenium long ago, and yet spectral lines matching technetium. Then promethium was reported, element 61 on the periodic table, entirely without stable isotopes, whose longest-lived isotope has a half-life of 17.7 years. Not millions of years, not thousands, 17 years. Then came reports of elements in the actinide series, evidence for actinium, protactinium, and in the most startling analyses, possible signatures consistent with plutonium, einsteinium, and fermium, synthetic transuranic elements that in terrestrial laboratories can only be produced in nuclear reactors, or the detonation of nuclear weapons, and that have half-lives ranging from hours to decades. Pause on that, really pause. If those identifications are correct, and I want to be honest here, and say that the heavier transuranic identifications remain contested because the spectral line databases for those exotic atoms are incomplete, and the analysis is genuinely difficult, then we are looking at a star that contains atoms whose very existence requires they were created recently, not cosmically recently, not within the last 100 million years recently. Recently in the sense that promethium with a 17.7-year half-life, if present in detectable quantities today, must have been produced within the last few thousand years at most. Elements with half-lives measured in decades cannot be remnants of the Big Bang. They cannot be leftovers from the star's formation. Whatever they are, they were made within the time span of recorded human civilization. There are several proposed explanations, and none of them are entirely satisfying, which is part of what makes this star so compelling to work through. The first, and astrophysically most conservative, invokes the chemically peculiar star mechanism in an extreme form. In magnetically peculiar A-type stars, like the AP stars we mentioned earlier, differential radiation pressure can cause heavy elements to levitate into the outer atmosphere and concentrate there, while lighter elements sink under gravity. The star's magnetic field can stabilize these concentration layers, creating photospheric patches of unusual chemical abundance. In this model, you're not seeing the bulk composition of the star, but a surface concentration effect, an atmospheric quirk. This is almost certainly responsible for some of the extreme rare Earth abundances in Przybylski's star. The problem is that this model explains stable element concentrations. It does not produce radioactive elements from nothing. Even the most exotic radiative levitation process cannot manufacture promethium. You still need a nuclear source. The second explanation invokes the R process, the rapid neutron capture process that produces the heaviest elements in neutron star mergers and some supernovae. Perhaps, the argument goes, HD 1165 was contaminated in the past by ejecta from a nearby stellar explosion, which seeded its outer layers with freshly synthesized heavy elements. This would explain the lanthanide overabundances beautifully. The R process is exactly the right mechanism for producing those elements. The difficulty with applying it to the short-lived radioactives is again time. An R process event close enough and recent enough to still show promethium in the spectrum would have to have occurred within the last few centuries. That is an improbably fortuitous coincidence. The third explanation has been advanced cautiously by a small number of researchers, and it invokes physics that sits at the very edge of what is currently confirmed, the theoretical island of stability in nuclear physics. Standard nuclear theory predicts that most transuranic elements are highly unstable, decaying within microseconds to days. However, nuclear models also predict the existence of specific combinations of protons and neutrons, magic numbers in the terminology of the field, that would produce isotopes of even very heavy elements with dramatically extended lifetimes. These predicted super heavy isotopes, around element 114 to element 126, might have half-lives not of hours, but of millions or even billions of years. If such long-lived super-heavy isotopes exist in nature, their spectral lines might superficially resemble those of the radioactive elements we have catalogued. We could be misidentifying the lines. What looks like promethium might be a long-lived isotope of an element with atomic number 113 or 115 or higher, an element for which we don't yet have a complete spectral database. This is not a fringe hypothesis. It is not the province of pseudoscience or speculation. The island of stability is a genuine prediction of nuclear shell theory, and the search for super-heavy elements is a serious ongoing area of experimental nuclear physics. The question is whether the cosmos can produce them in detectable quantities, and if it can, if the spectral anomalies in Przybylski's star are the fingerprints of elements we haven't fully characterized yet, then this single star, sitting 390 light-years from Earth in an unremarkable patch of southern sky, is evidence for nuclear physics that exceeds anything we can produce in our most powerful particle accelerators. This is, to my mind, one of the most consequential unresolved mysteries in all of modern astrophysics. Not because the answer is certainly dramatic, but because the range of possible answers is so wide. The conservative explanations, atmospheric concentration effects, ancient R process contamination, are plausible but imperfect fits. The extraordinary explanations, ongoing nuclear synthesis, island of stability isotopes, would require us to rewrite multiple chapters of nuclear and stellar physics. And the truth, whatever it is, sits in the spectrum of one star that an astronomer in Australia noticed 65 years ago had lines he couldn't name. The spectrum of HD 10165 has been analysed dozens of times by multiple research groups. With each improvement in instrumentation and atomic line databases, more features are identified, but more mysteries arise. As of the most recent comprehensive analyses, there remain spectral lines in Przybylski's star that match no known element, stable or unstable, literally unidentified lines. In a stellar spectrum in the 21st century, we can image the surface of neutron stars. We have mapped the cosmic microwave background to parts per million. We have detected gravitational waves from black hole mergers 1 billion light years away, and there is a star a short 4 centuries of light travel from home whose chemical composition we cannot fully explain. But Przybylski's star, confounding as it is at least a single object, sitting passively in its place, absorbing and re-emitting light in its peculiar way. It does not act, it does not move, it does not impose itself on the universe beyond its own neighbourhood. What comes next in our catalogue of rule breakers does all three, and it does them with an energy output that, for a fraction of a second, rivals the luminosity of 1 billion suns. On December 27th, 2004, at 21 hours, 30 minutes and 26 seconds Universal Time, every gamma-ray and X-ray telescope in orbit around Earth registered a signal so powerful it saturated their detectors. The pulse lasted for approximately 0.2 seconds, just over 1/5 of a second, but in that 1/5 of a second, the object that produced it released more energy than our Sun emits in 250,000 years. Not in X-rays alone. Total energy. In under 1/4 of a second, it outshone our Sun by a factor of more than 1 trillion. The source was not a nearby galaxy. It was not a supernova or a gamma-ray burst in the distant universe. It was a single object located on the far side of our own Milky Way, about 50,000 light-years from Earth. In a region near the constellation Sagittarius, it had a mass of approximately 2 solar masses. It occupied a sphere roughly 20 kilometers across, and its magnetic field, the field that powered this cataclysmic release, was somewhere in the region of 10-15 Gauss. That is 100,000 billion Gauss. For context, Earth's magnetic field measures roughly 0.5 Gauss. The field at the surface of this object was 2 quadrillion times stronger than the one that makes compasses work. The object was a magnetar. The specific designation is SGR 180620, and the event it produced on December 27, 2004 is known as the SGR 180620 giant flare. The effects were measurable here on Earth, from 50,000 light-years away. The initial surge of radiation struck our planet's ionosphere, the high-altitude layer of charged particles that radio waves bounce off, and deposited enough energy to ionize it to a depth comparable to what the most intense solar X-ray flares produce. For approximately 5 minutes, the dayside ionosphere of Earth, 50,000 light-years from the source, was measurably altered by this star's outburst. The event was detected by spacecraft and ground-based instruments across the full electromagnetic spectrum. The gamma-ray flux at Earth's location, after travelling 50,000 light-years through the thin interstellar medium, was still intense enough to perturb the planet's magnetic field by a detectable amount. Stop and think about that distance. 50,000 light-years. Light takes 50,000 years to travel that far. And at the end of that journey, this star's scream was still loud enough to ring our atmosphere like a bell. To understand how a magnetar produces this kind of energy, you first need to understand what a magnetar is. And to understand that, you need to understand neutron stars in general, because magnetars are, in the simplest structural sense, a subtype of neutron star, though calling them simply intense neutron stars is like calling a Category 5 hurricane a stiff breeze. When a massive star, say between 8 and 20 solar masses, exhausts its nuclear fuel and its core collapses, the inward implosion is halted not by thermal pressure, but by neutron degeneracy pressure, the quantum mechanical resistance of closely packed neutrons to further compression. The result is a neutron star, a ball of matter roughly 10 to 25 kilometers across, with a mass of 1 to 2 solar masses, composed almost entirely of neutrons packed to nuclear density. At that density, a single cubic centimeter of neutron star material would weigh roughly 400 million tons on Earth. The gravitational field at the surface is approximately 200 billion times stronger than Earth's surface gravity. An object the size of a city, more massive than the Sun. A neutron star retains the angular momentum and magnetic flux of its progenitor's collapsing core, but concentrated enormously by the shrinkage in volume. The collapse amplifies whatever magnetic field the star had before. In typical neutron stars, this produces surface magnetic fields in the range of 10e8 to 10e12 Gauss. Already extraordinary by any terrestrial standard, 1,000 times stronger than the most powerful permanent magnets humanity has ever constructed. These normal neutron stars, if they are rotating rapidly enough to produce a detectable sweeping beam of radiation, are called pulsars. Magnetars are something else. Theories of magnetar formation, still an active area of research, suggest that they arise either from extremely rapidly rotating neutron stars, in whose first seconds of existence a powerful convective dynamo amplifies the magnetic field to extraordinary levels, or possibly from the merger of two lower-mass neutron stars. Whatever the mechanism, the result is a neutron star with a surface magnetic field approaching or exceeding 10e15 Gauss. 3 orders of magnitude stronger than a typical pulsar. At those field strengths, physics becomes strange in ways that are difficult to fully appreciate. The magnetic field of a magnetar is strong enough to distort the electron clouds of atoms, stretching them into elongated shapes along the field lines. It is strong enough that the virtual particles produced and annihilated constantly in the quantum vacuum. Pairs of electrons and positrons that normally appear and vanish without consequence can be accelerated to relativistic speeds before they annihilate, producing real gamma-ray photons. The magnetic field itself contains an energy density comparable to or exceeding the thermal and gravitational energy of the neutron star it permeates, and that field is unstable. It shifts, it evolves. The crust of a neutron star is a layer of crystalline nuclear matter, roughly 1 kilometer thick, and when the interior magnetic field changes configuration, it stresses the crust. The crust cracks. These are starquakes, events analogous to earthquakes but releasing energies that make terrestrial seismology look like a child tapping a table. The December 2004 event from SGR 1806-20 was a giant flare associated with exactly this kind of catastrophic crust crack. A starquake that released the equivalent of 2 × 1046 ergs in total energy, a number written out as 2 followed by 46 zeros in units of centimeter-gram-second energy. For 5 months after the 2004 flare, SGR 1806-20 continued to produce smaller bursts detectable by orbiting telescopes. It has been quiescent since, its rotation slowly decelerating as the magnetic field breaks it, the way a spinning magnet loses energy by generating electromagnetic radiation. Magnetars are not permanent features of the cosmic landscape. They are young. The most active ones are typically less than 10,000 years old, and as they age, their fields decay and their bursting activity diminishes. The 28 known confirmed magnetars in the Milky Way are all young, all within the disk of the galaxy where active star formation occurs, all the products of massive star deaths that happened geologically recently. 28 confirmed magnetars in a galaxy of approximately 300 billion stars. These are vanishingly rare, and yet when they announce themselves, they do so with a voice that carries across the entire galaxy and still shakes our ionosphere at the far end of 50,000 light-years of empty space. What haunts me about magnetars is not the energy scale alone, though the energy scale is genuinely humbling, but the structural reality that they represent. In the cores of these objects, matter is so compressed and the magnetic field is so dominant that the physics operating there is not the physics you encounter in any other context in the observable universe. General relativistic corrections to the equations of nuclear matter are not optional refinements, they are the primary terms. Quantum electrodynamics operates in a regime, the strongly nonlinear regime, where the field strength exceeds the so-called Schwinger limit, that has never been reproduced in any laboratory and may never be. The interior of a magnetar is, in a real sense, inaccessible to direct experimental physics. We cannot build a magnetar in a test chamber. We cannot probe its surface with instruments. Everything we know about what is happening inside SGR 1806-20 is inferred from the radiation it emits, from models constructed by pushing known physics to its absolute boundary conditions. and from comparisons with other magnetars, whose behaviours provide independent checks. The magnetar is the universe's most extreme laboratory, and from 50,000 light-years away, it performs experiments in physics that we are not yet equipped to interpret fully. One question hangs over everything we know about magnetars, and it is this. If an ordinary collapsing massive star can produce a magnetar under the right conditions, how do we know that the conditions occurring in any given supernova are not those right conditions? How certain are we that a magnetar's formation is a rare aberration rather than a common endpoint that we simply detect rarely because most of them flare only briefly and then go quiet? And if magnetars are more common than we think, if the galaxy is full of cooling, silent magnetars whose active phases are long past, then what other phenomena, currently unexplained, might they be responsible for? But I am getting ahead of the story, because before we discuss the implications of rule-breaking stars for our understanding of the cosmos at large, I want to introduce you to the scientist at the centre of perhaps the most personal and revealing story this entire subject contains. A story about a hypothesis that its proposers expected to remain theoretical for the rest of their careers. A story about two stars that should not, by any conventional physics, be able to coexist. A story that, when confirmation finally arrived, changed everything it touched. In 1975, Kip Thorne was already famous. His contributions to the mathematical framework of general relativity had placed him in the first rank of theoretical physicists. Within a decade, he would be deep in the foundational work on gravitational wave detection that would eventually earn him a share of the Nobel Prize in Physics in 2017. He was, by any measure, a scientist operating at the summit of his discipline. His collaborator on the work they published together in 1975 was a young Polish astronomer named Anna Żytkow, who had been studying the evolution of compact objects and their interactions with stellar companions. The two were working through the implications of what happens when a neutron star, in a close binary system, spirals inward toward the outer layers of its red giant companion. This was not an exotic scenario. Neutron stars in binaries were known to exist. X-ray binaries had been observed, and the general behaviour of mass-transferring binary systems was understood in outline, if not in detail. What Thorne and Żytkow were doing was following the mathematics to its logical conclusion, past the point where most of their contemporaries had thought to look. Their question was stark. What happens if the mass transfer in a neutron star red giant binary does not reach equilibrium? What if, instead of the neutron star accreting material from the giant and settling into a stable X-ray binary configuration, the system enters a runaway in which the red giant's envelope expands, envelops the neutron star, and the two objects spiral together through a process called common envelope evolution? The mathematics told a clear story. If this happened, the neutron star, impossibly dense, roughly the size of a city, weighing twice as much as the Sun, would spiral into the interior of the red giant, deeper and deeper, converting its orbital kinetic energy into heat and puffing the giant's outer layers outward into space. At some point, the neutron star would reach the red giant's helium core, and there it would stop. Not because anything blocked it physically, but because the density of the helium core exceeds the density of the material the neutron star is being dragged through, changing the dynamics of the inspiral and allowing a stable configuration to form. The resulting object would be extraordinary. It would look from the outside like a very large red supergiant, bloated, cool, luminous, consistent in colour and spectral class with the known population of red supergiants in any galaxy. But inside it would be different from any other star ever modelled. Its energy source would not be nuclear fusion proceeding in a hot core, according to the standard stellar models. Its energy would instead come from accretion onto the neutron star at its centre, material from the giant's helium core falling inward toward the neutron star surface, releasing gravitational potential energy as heat. The neutron star would sit there, embedded in the stellar material like a seed inside a fruit, eating the star from the inside, powered by gravity instead of fusion, sustained not by the delicate equilibrium of radiation pressure and gravity that governs normal stars, but by a completely different physical mechanism. They called these hypothetical objects Thorne-Żytkow objects, or TZOs, in their 1977 follow-up paper, which refined the 1975 analysis and laid out the observational predictions in more detail. They noted that TZOs should be identifiable by distinctive chemical signatures in their spectra. The neutron star at the core would be hot enough to drive a specific pattern of nuclear reactions, an exotic process called the interrupted rapid proton process, or ERP process, that would produce anomalous concentrations of certain elements. In particular, TZOs should show elevated surface abundances of lithium, rubidium and molybdenum, elements that normal red supergiants produce in much smaller quantities. These chemical fingerprints were not just supporting evidence, they were the defining test. Thorne and Żytkow expected their prediction to remain hypothetical for a long time. Binary star evolution is common enough that TZOs ought to form at a non-trivial rate. Their estimates suggested perhaps 20 to 200 TZOs should currently exist in the Milky Way. But identifying them required knowing what to look for and having the spectroscopic sensitivity to find the chemical markers in the atmospheres of objects that otherwise looked like ordinary, unremarkable red supergiants. The theoretical prediction sat on the shelf of astrophysics for nearly 4 decades. Then, in 2014, an astronomer named Emily Levesque, working with a team that included Philip Massey at the Lowell Observatory, published a paper in the monthly notices of the Royal Astronomical Society letters that changed the conversation entirely. Levesque's team had been conducting a spectroscopic survey of red supergiants in the Small Magellanic Cloud, a satellite galaxy of the Milky Way sitting approximately 200,000 light-years from Earth. In their survey, one star stood out with striking chemical peculiarities. The star, catalogued as HV2112, showed a spectrum that included anomalously elevated concentrations of lithium, rubidium and molybdenum, specifically elevated, not a bit above normal, but elevated in the proportions and quantities that Thorne and Żytkow had predicted 37 years earlier for a star harbouring a neutron star core. The paper was cautious, as good science requires caution. Levesque and her co-authors noted that HV2112 was a candidate, not a confirmed TZO, and that alternative explanations, particularly the possibility that HV2112 was an asymptotic giant branch star in an unusual evolutionary phase, could not be ruled out. The scientific community received the paper with measured enthusiasm and significant skepticism. Several teams pointed out that the molybdenum and rubidium abundances, while unusual, could potentially be explained by standard stellar evolutionary models for sufficiently massive asymptotic giant branch stars. The debate continued. Subsequent analyses of HV2112 revised some of the initial abundance estimates. A 2018 study looking at a broader population of red supergiants in the Magellanic Clouds suggested that HV2112's chemical signature, while unusual, might not be unique enough to rule out conventional stellar models. Anna Żytkow herself, by this point in her 70s, and teaching at the Institute of Astronomy at Cambridge, was characteristically measured about the result. She had waited 40 years for even a candidate. She was not going to declare victory on the basis of one contested spectrum. But here is what I find most remarkable about the Thorne-Żytkow story. Not the object itself, not even the long wait for confirmation, but the sheer audacity of the original proposal. In 1975 and 1977, Thorne and Żytkow were describing an object that had never been observed. There was no empirical evidence for TZOs. There was no detection waiting to be explained. They were simply following the laws of physics, the equations governing stellar structure, neutron star physics, and binary evolution, to their logical endpoint and saying, if the equations are correct, this should exist. The object is a pure theoretical prediction, in exactly the same sense that general relativity predicted black holes before any were observed, in exactly the same sense that the Higgs boson was predicted 50 years before the LHC confirmed it, the existence of TZOs. even as candidates, even contested, even requiring further verification, tells us something specific and meaningful about the universe. It tells us that the endpoints of binary stellar evolution are stranger and more varied than our basic models account for. It tells us that a dead star, a stellar corpse with no living nuclear fire of its own, can persist for 1 million years or more by embedding itself inside a living star and feeding on it, powered not by fusion but by the most fundamental energy source in the universe, gravity. It tells us that two objects, a red giant spanning hundreds of millions of kilometers and a neutron star compressed into a sphere 20 kilometers across, can exist not as neighbors but as host and parasite, wrapped around each other, sharing the same stellar surface, categorically neither one thing nor the other. There is something philosophically provocative about this. We classify stars. We put them in bins, on diagrams, in categories that make our surveys tractable and our models computationally manageable. A TZO defies all classifications simultaneously. Is it a red supergiant? Its surface says yes. Is it a neutron star? Its core says yes. Is it alive in the stellar sense, powered by nuclear fusion? No. Is it dead in the stellar sense, cooling toward equilibrium? Also no. It is something the Hertzsprung-Russell diagram has no box for. I first worked through the Thorne-Żytkow papers, the original 1975 letter, and the longer 1977 analysis. I had to stop and sit with the mathematics for a while. The idea of a neutron star sitting inside a red giant, both objects simultaneously present, sharing a common gravitational center, each following its own physics and yet constituting a single observable entity. It stretches intuition past the comfortable range. And the fact that someone proposed it, rigorously and mathematically, 47 years before I am writing these words, and that the universe appears to have obliged by actually making one, seems to me the deepest kind of vindication that theoretical physics can receive. The search for confirmed TZOs is ongoing. The detailed modelling required to definitively separate a true TZO from an extreme asymptotic giant branch star requires spectroscopy at resolutions that are only now becoming routine with the latest generation of large aperture telescopes. The extremely large telescope, currently under construction in the Chilean Atacama Desert, and expected to begin scientific operations in the late 2020s, will have spectroscopic capabilities precise enough to distinguish the IRP process elemental signatures from conventional AGB star chemistry with far greater confidence than current instruments allow. Anna Żytkow, who spent a decade without seeing her theoretical prediction receive any observational attention, may yet live to see it confirmed beyond reasonable doubt. And if it is confirmed, when it is confirmed, then the universe will have demonstrated something extraordinary, that inside the red supergiant stars scattered across galaxies, there are objects powered not by the same thermonuclear fires that light our sun, but by a neutron star's gravitational appetite, quietly eating the star from within for millions of years, invisible to any method of observation except a careful analysis of exactly which elements its surface contains, in exactly what proportions, a star swallowed from the inside. An impossible compound object, predicted by mathematics and apparently constructed by the universe. There is a particular quality to anomalies that are discovered not by professional astronomers with dedicated research programs, but by ordinary people looking at data in their spare time. There is a humility to it, and a democratizing strangeness. The Kepler Space Telescope, launched in March 2009, produced what was by any measure one of the most consequential astronomical datasets of the 21st century. Precise, continuous photometric measurements of the brightness of approximately 150,000 stars over a period of 4 years. Kepler was looking for planets. The method was transit photometry. If a planet passes in front of its host star from Kepler's perspective, it blocks a small fraction of the star's light, producing a tiny, regular dip in the brightness curve. By monitoring 150,000 stars simultaneously, Kepler was statistically guaranteed to capture planetary transits from a significant number of them. The dataset this produced was too large for professional astronomers to analyse manually. So NASA, in collaboration with the Zooniverse citizen science platform, launched a project called Planet Hunters, in which volunteers from around the world were shown visualizations of Kepler light curves and asked to flag anything that looked anomalous. Hundreds of thousands of people participated. Most of the anomalies they flagged turned out to be instrumental artifacts, variable stars, or eclipsing binary systems, all known phenomena with well-understood explanations. But in 2011, a small group of citizen scientists, amateur astronomers, hobbyists, people who had signed up to help find exoplanets on their lunch breaks, flagged a light curve from a star designated KIC 8462852 as interesting, using that word in its scientific meaning rather than the vague colloquial sense. The flag was correct. KIC 8462852 would prove to be the most anomalous stellar light curve in the entire Kepler archive. Tabetha Boyajian was a postdoctoral researcher at Yale University when the Planet Hunters volunteers began accumulating their flags on KIC 8462852. She was, by her own account, initially skeptical that the anomaly would prove significant. The photometric pipeline for Kepler data was full of systematic errors and instrumental quirks, and unusual-looking light curves frequently resolved into mundane explanations on closer examination. But the flags on KC 8462852 were persistent and systematic, and when Boyajian's team began a detailed analysis of the star's full 4-year light curve, the result was, to use her own carefully chosen language in the paper they published in 2016, bizarre. KC 8462852 is an F-type main sequence star approximately 1,470 light-years from Earth, roughly 1.46 times the mass of our Sun, 1.58 times its radius, and with a surface temperature around 6,750 Kelvin. In all structural respects, it is an ordinary, unremarkable star, a member in good standing of the main sequence, doing what F-type stars do, burning hydrogen quietly in its core. There is nothing in its basic parameters that predicts what its light curve shows. A normal planetary transit produces a clean symmetric dip in the stellar brightness, a precise, repeating reduction of light lasting hours to days, with a depth proportional to the ratio of the planet's area to the star's area. For an Earth-like planet transiting a Sun-like star, the dip depth is roughly 0, rho 8%, barely detectable, requiring the precision of space-based photometry. For a Jupiter-sized planet, the dip reaches about 1%. These dips are smooth, periodic, and predictable. The dips in KIC 8462852's light curve were none of those things. They were asymmetric, with faster ingress than egress, suggesting irregular shapes rather than circular disks. They varied in depth from less than 1% to over 22%. A 22% dimming means something was blocking more than a fifth of the star's visible disk, which no known planet-sized object could accomplish for a star of this size. They were not periodic in any pattern consistent with a stable orbiting body. They clustered in complex groupings, with multiple overlapping dip events, suggesting either multiple objects or a single object of extraordinarily irregular geometry. And they were scattered throughout the 4-year baseline in a way that made it impossible to assign a simple orbital period. The 22% dip in particular deserves to be held still and stared at. For context, the largest planet in our solar system, Jupiter, blocks roughly 1.1% of the Sun's light during transit. To block 22% of the light from KIC 8462852 would require an object, or a collection of objects, with a cross-sectional area approximately 20 times Jupiter's. In our solar system, no such object exists. No planet, no moon, no asteroid field, nothing. 20 times Jupiter's area is a number that sits firmly outside the parameter space of normal planetary science. Boyajian's 2016 paper, authored with 40 co-authors, drawn largely from the Planet Hunters citizen scientist community, an authorship list that itself represents something new in the history of science, laid out the observational data, and systematically eliminated the most obvious explanations. Instrumental artifacts could not explain the signal because multiple independent analysis methods confirmed it. Star spots, dark regions on the stellar surface, could not produce dips of this depth or this shape. Binary star interactions could not produce the correct pattern. A catastrophic collision between large bodies in the planetary system was proposed and partially entertained, but the dust cloud produced by such a collision should have been detected in infrared observations, and surveys found no infrared excess consistent with the required dust mass. Then came the paper from astronomer Jason Wright at Penn State, who co-authored a paper pointing out, with appropriate scientific qualification, that the light curve was consistent with the kind of occultation pattern you would expect from a Dyson swarm, a theoretical structure in which a civilization harvests stellar energy by placing large numbers of orbiting structures around their star, structures that would collectively block starlight in exactly the kind of irregular, variable, non-periodic way observed in KIC 8462852. Wright and his co-authors were explicit that this was the least likely explanation and that any natural explanation, however exotic, was far more probable. But in the popular press, the damage was done. KIC 8462852 became Tabby's star after Tabitha Boyajian, and it became the alien megastructure star, a phrase that does precisely the wrong thing to public understanding of how scientific hypotheses are supposed to be evaluated. Boyajian was, by her own account, frustrated by this. She had not proposed the alien megastructure hypothesis, and she had never considered it a credible scientific possibility. But the attention it brought also brought resources. In 2016, she ran a Kickstarter campaign, a crowdfunding campaign for a scientist watching a star, raising more than $107,000 to fund a dedicated observational campaign using the Las Cumbres Observatory, a network of robotic telescopes distributed across multiple continents. The campaign allowed real-time, multi-wavelength monitoring of the star, so that if it dimmed again, a team would be watching with enough instruments to characterize the event in detail. The star dimmed in May 2017. Boyajian's network caught it in real time. The data collected during the 2017 dimming event ultimately provided the most important observational clue yet to the star's behavior. The dimming was wavelength dependent. The star faded more strongly at shorter, bluer wavelengths than at longer, redder ones. That single fact is decisive. If the dimming were caused by a solid opaque object, a planet, a megastructure, a large collection of solid debris, the dimming would be achromatic. The object blocks all wavelengths of light equally, because it is simply in the way. Wavelength-dependent dimming, where blue light is preferentially blocked, is the signature of fine dust particles. Particles small enough that they scatter shorter wavelengths more effectively than longer ones. Not solid objects. Dust. This is the leading current explanation for the short-term dipping in KIC 8462852. Circumstellar dust clouds of irregular geometry, composition and density, orbiting the star in clumps and streams. The dust is probably the remnant of a disrupted body, a large comet, a shattered planetesimal, possibly the debris of a recent planet-planet interaction that sent icy bodies raining inward toward the star. The irregular dipping pattern reflects the irregular, non-circular distribution of dust in the system. But there remains a second, longer timescale anomaly that dust alone does not easily explain. Reanalysis of photographic survey plates from the Harvard Plate Collection, which contains stellar observations stretching back to the 1890s, revealed that KIC 8462852 dimmed by approximately 0.9% per year over the century from 1890 to 1989, a secular decline in brightness totaling roughly 16% over a century. More recent analysis of data from the DASC program, which digitized and analyzed the full Harvard Plate archive, confirmed this long-term secular fading, though the exact magnitude and interpretation remain subjects of active debate. A sustained, century-long fading cannot be explained by an orbiting dust cloud, which would produce a periodic or quasi-periodic signal, not a monotonic secular decline. Some researchers have proposed that the star is gradually consuming a disrupted planetary body, accreting material from a shattered planet or large comet, with the accreted material temporarily cooling and dimming the outer stellar layers. Others have suggested that the star's magnetic activity cycle, playing out over decades rather than the roughly 11-year cycle of our Sun, could produce long-term brightness changes. None of these explanations is entirely satisfying. KIC 8462852 is the star that taught us something specific and important about how science works in the 21st century. It was found not by a funded research program, but by volunteers. It was studied not just by professional teams with access to telescope time, but by a crowd-funded observational campaign financed by people who were curious. The paper announcing its discovery carries 41 authors, many of them with no formal astronomical training, and it has not been explained, not fully, not cleanly, not in a way that closes the question and moves on. The universe is not obligated to be legible. KIC 8462852 may be a perfectly natural star exhibiting a combination of perfectly natural phenomena that we have not previously seen assembled in this configuration. The secular fading and the irregular dipping may have separate explanations, unconnected to each other, or they may both be consequences of a single underlying process that we have not yet identified. The honest answer, as of this writing, is that we do not know. The star continues to vary, the observations continue to accumulate, the explanation continues to resist clean formulation, and that is, in its own way, most important thing a star can be: not explained, not resolved, not filed and categorized, still asking a question. We have met 5 families of stellar rule breakers now, and the time has come to ask the harder question. Not what are they, but what does their existence mean? Not the surface interpretation, that the universe is strange, that nature is creative, but the deeper structural question. What do anomalous stars tell us about the gaps and fault lines in our framework for understanding how stars work? The answer is more unsettling than a simple catalogue of curiosities suggests. Begin with what stellar physics actually is, at its foundation. The standard theory of stellar evolution, sometimes called the canonical model or the standard stellar model, is a framework built on a specific set of physical assumptions. Stars are spherically symmetric objects. They are in hydrostatic equilibrium, meaning the pressure gradient at every point in the interior exactly balances the gravitational force pulling material inward. They evolve smoothly and deterministically, their structure at any moment determined by their mass and chemical composition. Their internal processes, nuclear reactions, convection, radiative diffusion, are well characterized by terrestrial laboratory physics, scaled to stellar conditions. This framework works extraordinarily well for the vast majority of observable stars. It correctly predicts the main sequence, the turn-off points of stellar clusters, the luminosities and temperatures of red giants and horizontal branch stars, the masses of white dwarf remnants, the properties of neutron stars produced in supernovae. Its successes are not trivial. They are among the most precisely verified predictions in all of natural science. But the framework has assumptions built in that are, to a greater or lesser degree, idealizations. Real stars are not perfectly spherical. Rotation flattens them, and the most rapidly rotating stars, spinning at fractions of their breakup velocity, are significantly ablate. Real stars are not always in strict hydrostatic equilibrium. Pulsating variables, stellar oscillations, mass transfer events, all represent deviations from strict equilibrium. Real stars do not always evolve in isolation. Binary companions, cluster dynamics, tidal interactions, and accretion events all perturb the canonical evolutionary track. Blue stragglers exist because the standard model is a single-star model. Its predictions are correct for isolated stars, evolving without external interactions, but the real universe is full of binary systems. Approximately half of all solar-type stars in the galaxy are members of binary or multiple star systems. In the densely packed cores of globular clusters, the fraction of stars that have experienced dynamical interactions, close encounters, tidal captures, exchanges in hierarchical triples is even higher. The single-star model is not wrong. It is incomplete. It handles the case that most applies to most stars most of the time. and blue stragglers are the visible reminders that the other case. The interacting binary, the merging system, the mass-transferred compound produces outcomes the canonical model was not built to predict. This is a specific type of scientific incompleteness. It is not that the underlying physics is wrong, but that the model's boundary conditions are too restrictive. The physics of mass transfer in binary stars is well understood. The Roche-Loeb overflow is calculable. The accretion process is modelled. What was lacking, for decades after Sandige's discovery, was the empirical confirmation that binary evolution was the dominant pathway for blue straggler formation in open clusters, and that confirmation required the kind of painstaking 20-year radial velocity survey that Mathieu and Geller conducted at Boyajian. Science does not always lack the theory. Sometimes it lacks the patience to assemble the evidence. Thorne Żytkow objects represent a different category of incompleteness. Not a failure of the single-star model, but a failure of imagination about what binary evolution can produce. The canonical model for neutron star binaries considers the neutron star and its companion as persistent, separate entities. The neutron star accretes from the companion's stellar wind or through Roche-Loeb overflow, but the two objects remain distinct. The model stops at the point where common envelope evolution begins, and the neutron star begins to spiral inward, because following the mathematics past that point leads to a conclusion that feels intuitively wrong, that a neutron star can be incorporated into a stellar interior and continue to exist there. The intuitive wrongness is not justified by any physical argument, it is just unfamiliar. And Thorne and Żytkow, by following the mathematics without flinching, arrived at a prediction that the universe appears to have honoured. There is a lesson here that applies far beyond stellar physics. Our theoretical frameworks are not just collections of equations. They are collections of assumptions about what kinds of outcomes are plausible, and those assumptions are infected by the observer's intuitions about what seems natural and what seems too strange to take seriously. Thorne and Żytkow proposed TZOs precisely because they were willing to follow the equations into territory that felt strange. Anna Żytkow spent 40 years waiting for observations to catch up to the mathematics. That patience, that willingness to sit with a prediction that no one had confirmed, is itself a form of scientific courage. Magnetars present a problem of a different character entirely. They do not represent a failure of the single-star model exactly, because magnetars are the remnants of single massive stars, or at least the most straightforwardly formed magnetars appear to be, but their existence points to a gap in our understanding of the magnetic field amplification process during core collapse, which has significant implications for every model of neutron star formation. The standard picture of core collapse assigns the neutron star's magnetic field from conservation of the progenitor's field during collapse. The field is compressed along with the matter, amplifying by a factor roughly equal to the ratio of the stellar core's initial to final radius squared. For a typical massive star core collapsing from a radius of a few thousand kilometers to a neutron star radius of about 10 kilometers, this gives amplification by a factor of roughly 10 billion, which, applied to a solar-type magnetic field, produces the normal neutron star field range of 10.8 to 10.12 Gauss. Magnetars with fields at 1014 to 1015 Gauss require an additional amplification of 2 to 3 orders of magnitude beyond this. The leading mechanism is the millisecond magnetar scenario, a neutron star formed with an initial rotation period of 1 to 3 milliseconds. Comparable to the sub-millisecond oscillation timescale of fluid instabilities in the collapsing core, can support a powerful convective dynamo in its first few seconds of existence. The differential rotation and convection in the newly formed neutron star amplify the seed magnetic field by the same mechanism that solar and planetary dynamos work, but with the parameters dialed to their most extreme values. This alpha-omega dynamo, operating for just seconds at the temperatures and densities of a newborn neutron star, can amplify the field to magnetar levels before the rotation decelerates. The problem is that this mechanism requires the progenitor core to be rotating rapidly, very rapidly, and in most massive stars, the outer layers are expected to carry away angular momentum through stellar winds and mass loss before the core collapses, leaving the core relatively slowly rotating. Magnetar formation, therefore, requires either a specific subset of stellar evolutionary histories, stars that retain angular momentum in their cores better than the canonical model predicts, or a different amplification mechanism entirely. Several current theoretical proposals invoke the Kelvin-Helmholtz instability at the interface between the proto-neutron star and the accreting material from the failed shock, or convective overshoot from the surface of the proto-neutron star into the surrounding material. None of these mechanisms are ruled out. None of them are confirmed beyond doubt. The 28 known magnetars in the Milky Way are a very small sample from which to discriminate between these formation scenarios. Each new magnetar detected adds a data point, but the parameter space, progenitor mass, rotation rate, metallicity, binary history, is large enough that a definitive observational test remains out of reach with current samples. What Przybylski's star reveals about astrophysical incompleteness is the most fundamental of all. If the radioactive elements in its spectrum are real, if the promethium and technetium detections are not artifacts of misidentified spectral lines, then the star contains ongoing or very recent nucleosynthesis of elements that the standard model of stellar nucleosynthesis does not predict in any known stellar environment. The S process, which occurs in the thermal pulses of asymptotic giant branch stars, produces heavy elements via slow neutron capture, but it does not produce elements beyond bismuth in significant quantities, and it does not produce short-lived radionuclides in the quantities apparently seen in HD 165. The R process, which produces the heaviest elements in neutron star mergers and some supernovae, is not expected to be ongoing in a slowly rotating, photometrically stable, apparently quiescent AP star in the southern sky. The island of stability hypothesis, for all that it sits on the fringes of mainstream astrophysics, has a genuine scientific pedigree. The nuclear shell model predicts that closed shell nuclei, those with magic numbers of protons and neutrons, particularly around the doubly magic combination of 114 protons and 184 neutrons, should be dramatically more stable than the trend from lighter nuclei predicts. The heaviest elements produced in terrestrial particle accelerators to date have been synthesis of elements up to oganesson, element 118, but these have been produced in single atom quantities and have half-lives of milliseconds to seconds. Theorists predict that super-heavy nuclides with the right closed-shell configurations could have half-lives millions of times longer, long enough, potentially, to persist in stellar atmospheres, if such long-lived super-heavy isotopes exist naturally, formed in the R process of neutron star mergers and surviving for geological timescales. Then a chemically peculiar star whose atmosphere concentrates heavy elements via radiative levitation could accumulate visible quantities of them. The spectral lines of these isotopes are unknown experimentally. We have never produced them in quantities large enough to measure their transitions. In principle, they could be responsible for unidentified lines, not just in Przybylski's star, but in other AP stars. We would have no way to know without a nuclear physics program specifically designed to measure super-heavy element spectra. This is, I find, one of the most genuinely exciting frontiers in contemporary physics. The possibility that a single peculiar star in the southern sky might be our best observational evidence for nuclear physics, operating in a regime that our best accelerators have never reached. The answer might not come from a bigger telescope. It might come from a more powerful particle accelerator producing longer-lived super-heavy isotopes in quantities large enough to measure their spectral properties. The astrophysical anomaly and the nuclear physics experimental program are, on this reading, different facets of the same investigation. Boyajian star KIC 8462852 sits in a category that is distinct from the others we have examined. It is not an intrinsically exotic type of stellar object. but a normal star in an apparently abnormal environment. The star itself follows all the rules. Its mass, luminosity, temperature, and spectral type are all consistent with standard stellar models for an F-type main sequence star. What is anomalous is what is around it: the cloud of dust, the secular fading, the non-periodic dimming events. In this sense, KIC 8462852 is the rule breaker that breaks the rules not by being fundamentally different from normal stars, but by being a normal star in an abnormal situation. This distinction matters because it suggests that the category of anomalous stars is broader than it first appears. Many of the objects we classify as rule breakers are anomalous not because the star itself has unusual internal physics, but because the star's environment, or history, or companions, or host cluster has placed it in a configuration that the standard model does not predict. Blue stragglers are normal stars that have received extra mass. TZO candidates are normal red supergiants that have swallowed abnormal companions. Boyajian star is a normal F-type star that is surrounded by a debris cloud with unusual properties. The exception is Przybylski's star, which appears genuinely, intrinsically anomalous, whose spectrum cannot be entirely explained by any environmental or historical factor, and whose anomalies point inward to the star's own composition. And Magnetars, which represent the extreme tail of a distribution in compact object properties that standard physics allows but does not comfortably accommodate. There is a pattern in this taxonomy. The anomalous stars cluster around the interfaces between single star and binary evolution, blue stragglers, between living star and stellar remnant, TZOs, between nuclear synthesis and nuclear stability, Przybylski's star, between stellar evolution and stellar environment, Boyajian star, between ordinary neutron star and exotic compact object, Magnetars. These are the seams in our theoretical framework, the places where one model stops and another begins, where the idealizations built into each model are most likely to break down. And there is a further point that has not been made explicitly yet, but which I think deserves to be stated clearly. Every one of the rule-breaking categories we have discussed was discovered by accident. None of them were predicted before observation. Alan Sandage was not looking for stellar age anomalies, he was doing routine photometry. Przybylski was not looking for exotic nucleosynthesis, he was classifying stellar spectra. The Planet Hunters volunteers were not looking for anomalous secular dimming, they were flagging transit signals for an exoplanet survey. The December 2004 Magnetar flare was not anticipated. It saturated detectors that were not pointed at SGR 1806-20, but happened to be in a geometry where the radiation struck them. Each discovery of a rule-breaking star has expanded the catalogue of things we know exist but did not predict. And each expansion of that catalogue has raised, rather than answered, the central question of stellar astrophysics. Are there categories of anomalous stellar objects that we have not yet discovered, whose existence is perfectly consistent with known physics, but whose parameters place them outside the range of our current observational surveys? The answer, almost certainly, is yes. In November 2022, a team led by Kareem El-Badri at the Harvard-Smithsonian Center for Astrophysics published a paper describing a remarkable detection. Using astrometric data from the European Space Agency's Gaia satellite, cross-referenced with radial velocity measurements from the Lamost spectroscopic survey, they had identified a binary system, a star and a companion, in which the companion was completely invisible at all observed wavelengths. The system, designated Gaia BH1, lies approximately 560 light-years from Earth in the constellation Ophiuchus. The visible component is a solar-type G-type star. The invisible companion has an inferred mass of approximately 9.62 solar masses, derived entirely from the gravitational influence it exerts on the visible star's orbit. 9.6 solar masses is too large for a white dwarf, which cannot exceed about 1.4 solar masses, far too large for a neutron star, which caps out around 2 to 3 solar masses. The invisible object is by mass a stellar mass black hole, and it is not radiating detectably in any wavelength band. No X-ray emission, no radio emission, no optical emission. It is a dormant black hole, a stellar mass black hole in a binary system that is currently not accreting material from its companion at a rate sufficient to produce detectable radiation. This sounds like a reasonably comprehensible discovery. A dormant black hole. Fine black holes exist, we know this. But the significance lies in the phrase dormant black hole in a binary system with a sun-like star. In conventional stellar evolution models, forming this system is extremely difficult. The black hole must have been a massive star, at least 20 or 30 solar masses, before it collapsed. Massive stars produce powerful stellar winds and lose substantial mass throughout their lives. Before collapsing, they expand into supergiants. The binary system would have had to survive the supernova or direct collapse that formed the black hole, with the two objects remaining bound, despite the mass loss and kick velocity from the explosion. And the current separation must be consistent with the companion star surviving the progenitor's supergiant phase. If the two objects were too close during that phase, the companion would have been engulfed. The current orbital period of Gaia BH1 is 185.6 days. At that period, and with those masses, the black hole and the sun-like star are separated by about 1.4 astronomical units, roughly the distance from Earth to beyond Mars. The surviving companion star shows no sign of disturbance or unusual chemistry. It is an entirely ordinary solar-type star, sitting 1.4 astronomicals from a 9.62 solar mass black hole, completing its orbit every 185 days in a system that should, according to the standard binary evolution models, have either merged or been disrupted by the formation of the black hole long before it were reaching its current configuration. Gaia BH1 was followed by Gaia BH2, reported in 2023, at a similar distance from Earth and with similar properties, and by Gaia BH3 announced in 2024, which at approximately 33 solar masses, is the most massive stellar mass black hole known in the Milky Way. In 3 discoveries spanning fewer than 2 years, using the exquisite astrometric data from Gaia, the census of dormant stellar black holes in binary systems went from 0 to 3. The implications are statistical as much as physical. For 3 systems to be found within this distance in this time suggests that dormant black hole binaries are far more common in the Milky Way than the standard binary evolution models predicted. The standard models struggled to form even one such system without disrupting the binary. 3 within 1,560 light-years of Earth implies, by simple Poisson statistics, assuming the systems are not clustered in our neighbourhood, that there are likely many hundreds, possibly thousands of similar dormant black hole binaries distributed across the galaxy. That is a population of objects that was essentially invisible before Gaia's astrometric precision was available. And the existence of this population raises an immediate and uncomfortable question. What else is out there that we have been unable to detect, not because it doesn't exist, but because our instruments were not sensitive enough to find it? The current generation of large-scale surveys, Gaia, the Vera-Rubin Observatory, the Square-Kilometre Array radio telescope under construction in South Africa and Australia, are designed to scan the sky with a thoroughness and sensitivity that previous generations could not approach. Gaia alone has measured the precise positions and proper motions of approximately 1.46 billion stars. The Rubin Observatory, when it begins its legacy survey of space and time in the late 2020s, will detect changes in stellar brightness and position at a cadence and depth that will effectively turn the entire southern sky into a real-time variable star survey. The SKA at full operation will have a radio collecting area of approximately 1 square kilometre, roughly 50 times larger than any existing radio telescope, and will scan the sky with sensitivity sufficient to detect pulsars, magnetars, and radio transient phenomena at distances and rates never previously possible. Within these surveys, what rule-breaking stars will we find? The question is not rhetorical. There are specific predictions that can be made and specific categories of anomalous object that current theory predicts should exist but that we have not yet confirmed. The complete census of TZOs, if they exist in the numbers Thorne and Żytkow estimated, 20 to 200 in the Milky Way, should become accessible through the combination of spectroscopic surveys at current 8 to 10 metre class telescopes and the eventual 39 metre collecting area of the extremely large telescope. The ERP process chemical signature of rubidium, lithium and molybdenum overabundances is theoretically distinctive enough to identify TESO candidates in large-scale spectroscopic catalogues, provided the survey coverage reaches the distant obscured regions of the galactic disk where massive stars preferentially live. We may be 6 to 8 years away from a census of confirmed TZOs, and the number will tell us something critical about common envelope evolution, about how often the neutron star in spiral scenario completes versus being disrupted. The population of anomalous magnetic stars, including Przybylski's star analogues, is currently constrained to the relatively small sample of well-studied AP stars in the solar neighbourhood. The full-sky spectroscopic surveys, enabled by the foremost and weave fibre spectrographs, both operating in the mid-2020s, will characterise the spectra of tens of millions of stars at resolutions sufficient to detect heavy element anomalies. If the Przybylski star phenomenon is rare, the expanded survey sample will define its frequency and distribution with precision. If it is more common than currently thought, if the solar neighbourhood has been surveying a representative but small slice of a larger, chemically diverse ape population, then the surveys will reveal it. For Magnetars, the SKA's radio pulsar survey is expected to increase the known population of radio pulsars in the Milky Way from the current approximately 300 to potentially over 10,000, including the detection of pulsars in the galactic centre region currently inaccessible to existing radio telescopes due to the absorbing effects of the intervening interstellar medium. Magnetar candidates should be detectable among these new pulsars through their characteristic spin-down rates and X-ray burst histories. A statistically robust magnetar census, with hundreds of objects rather than tens, would finally discriminate between the competing formation models and tell us whether magnetars represent 1% or 10% of all neutron stars produced in the galaxy. There is another category of anomalous star that deserves mention here because it sits at the intersection of multiple rule-breaking phenomena and may represent a new class that we are only beginning to understand. These are the long-period radio transients, objects that produce bursts of radio emission at intervals of minutes to hours, with pulse profiles unlike those of known pulsars and properties that don't fit comfortably into any existing category of compact object. The first of these, Gleam XJ162759.55235.4.3, was discovered in 2022 and pulses every 18.18 minutes, with a radioluminosity that places it far above the radio-emitting death line for normal pulsars, a line below which, according to standard pulsar physics, radio emission should be impossible. The second, GPM J8839-10, was discovered in 2023 and has a period of 21 minutes, and analysis of archival radio data reveals that it has been detectable for at least 33 years, 21 minutes. A compact object, almost certainly a neutron star or white dwarf, producing radio pulses every 21 minutes. This is orders of magnitude longer than the longest known radio pulsar periods, which top out around 76 seconds. Standard pulsar deathline theory says that at this rotation rate, the radio emission mechanism should have long since failed, and yet there they are, pulsing with metronomic regularity at intervals of 21 minutes for over 3 decades. The proposed explanations range from ultra-long period magnetars rotating so slowly that they sit far below the conventional deathline, but whose strong magnetic fields power a different emission mechanism, to white dwarf pulsars in which the much weaker magnetic field of a rotating white dwarf generates radio emission through a mechanism different from neutron star pulsars. Neither explanation is fully satisfying. Ultra-long period magnetars are not predicted to produce the radio emission profiles observed. White dwarf pulsars have been proposed before, but only one confirmed candidate exists, AR Scorpii, which operates at a different frequency and luminosity regime. These long-period transients are the newest anomalies in the stellar Rule Breaker catalogue. They were found by a new generation of radio telescopes conducting wide-field surveys, the Meerkat Telescope in South Africa and the Murchison Wide Field Array in Western Australia, that see the radio sky at cadences and sensitivities that previous instruments could not match. The discovery of two such objects within 2 years of each other strongly implies the existence of a population, and if a population exists, the SKA will find it in the thousands. What those thousands of objects turn out to be, what physical mechanism makes a compact object pulse with a 20-minute period for decades, is a question that currently has no agreed answer and may require the addition of a new category to the taxonomy of stellar remnants. The Vera Rubin Observatory will conduct its LSST survey over a 10-year baseline, imaging the entire southern sky every 3 nights and accumulating a database of time-domain photometry for approximately 20 billion sources. Every variable source in the southern sky, every star that changes brightness, every transient that flares and fades, every periodic dimmer and brightener will be captured in this survey with a completeness that no previous instrument has approached. When those 20 billion light curves are analysed, a task that will require machine learning algorithms operating at the scale that no human team could manage manually, the catalogue of stellar anomalies will almost certainly expand dramatically. There will be more Boyajian stars, more stellar light curves exhibiting dimming patterns that don't match any known phenomenon, more stars whose secular behaviour reveals a process we haven't named yet. The universe has been performing these experiments for billions of years. We have been watching carefully for decades, and every time our instruments improve by an order of magnitude in sensitivity or coverage, we find new things that the previous instruments could not detect. The discoveries of Gaia BH1, BH2 and BH3 in the space of 2 years, the long-period radio transients, the exquisite detail now available in Blue Straggler binary populations. These are not the end of a catalogue, they are the beginning of one. There is a specific, important question that the next generation of surveys will be positioned to answer, and it is this: are the anomalous stars we currently know, the Blue Stragglers, the TZOs, the Magnetars, the Przybylski's stars, the complete set of anomalous stellar categories, or are they the visible tip of a much larger iceberg of stellar rule-breaking that current instruments cannot detect? The historical record is unambiguous on this question. Every time astronomy has significantly improved its observational capabilities, it has found new classes of object that no prior model predicted. Radio astronomy in the 1960s found pulsars. X-ray astronomy in the 1970s found magnetars and X-ray binaries. Gravitational wave astronomy in the 2010s found black hole merger populations whose mass distribution surprised everyone. Survey astronomy in the 2020s found dormant black hole binaries. There is no compelling theoretical argument that we have reached the end of this sequence of surprises, and there is every empirical reason to expect that the next generation of instruments will find the next generation of impossible stars. There is something that I keep returning to when I think about all the stars we've walked through in this story. It is not the energy of a magnetar flare, or the chemical impossibility of Przybylski's spectrum, or even the quiet audacity of a dead neutron star settling into the interior of a living red giant and making a home there. Those are the dramatic facts, and they deserve their drama. What I keep returning to is simpler. It is Alan Sandage in 1953, sitting at his measuring engine in the darkened room at Mount Palomar, looking at a photographic plate of Messier 3 and seeing something that should not be there. He would have known immediately, with the intuition of a physicist who has spent years learning what the Hertzsprung-Russell diagram means, that the blue star in front of him was wrong, was occupying a position in colour magnitude space that the cluster's age made impossible. He did not call it a discovery. He named it a straggler, the way you describe someone who arrived late to their own funeral, who turned up after the roll call had already been taken and the door had already been locked. There is something profound in that name. Not the anomaly, the straggler, the thing that didn't keep up with what it was supposed to do. There is almost an affection in it, a scientist acknowledging not that the universe has made an error, but that it has made a choice, that the rules for this star were negotiable. We build our models because we must. Without the framework of stellar physics, without the Hertzsprung-Russell diagram, the standard stellar evolutionary tracks, the nucleosynthetic predictions, the neutron star equation of state, we would have no way to approach the vast, silent complexity of a galaxy containing hundreds of billions of stars. The model is an act of compression, of making the comprehensible world smaller so that human minds can hold it. The model is not the universe, it is a map, and like all maps, it leaves things out. The rule-breaking stars are the things the map leaves out, and they are not failures of the map. They are invitations to revise it. Every anomalous star, every blue straggler, every TZO candidate, every magnetar that rings our ionosphere from 50,000 light-years away, every star with impossible elements burning in its outer layers, is the universe delivering evidence that the current version of the map is good but not complete. The evidence is offered without commentary. The stars do not announce themselves as counterexamples. They sit where they are, doing what they do, and wait for someone to look closely enough to notice that something is wrong. The human story embedded in stellar astrophysics is, at its core, the story of noticing. Sandage noticing, Przybylski noticing, Thorne and Żytkow following the mathematics past the comfortable stopping point and noticing what was on the other side. Boyajian noticing that the flags placed by volunteers on a crowdfunding citizen science platform deserved a paper, deserved a campaign, deserved the sustained attention that would eventually extract a physical answer from years of data. The tools have changed, from photographic plates to silicon detectors to space-based astrometry to neural networks analysing 20 billion light curves simultaneously, but the act has not. Someone looks at something that everyone else has seen and notices that it doesn't fit, and then the hard, slow, collaborative work of understanding begins. I will admit, and I mean this without rhetorical embellishment, that writing this has left me with a feeling that I find difficult to exactly name. It is something adjacent to humility but warmer than humility. The knowledge that the universe is larger in possibility than any single framework contains is, in one reading, a troubling fact. It means our models are always incomplete, always one discovery away from requiring revision, but in the reading I prefer, it is the most liberating fact in science. It means the work is never done. It means that the next person to sit down at a measuring machine, or a spectral analysis pipeline, or a machine learning classifier running on 20 billion light curves, and notice something that doesn't fit might be holding the key to a new category of existence that no one has named yet. We have met the outlaws of stellar physics. We have seen what they do to our models, what they demand of our imaginations, what they suggest about the richness of a universe that has been running stellar experiments for 13 billion years without consulting us about which outcomes it was allowed to produce. The catalogue is not closed. The blue stragglers will keep burning in their old clusters, wearing their stolen youth, for billions of years to come. The Magnetars will keep spinning down in the galactic disk, their fields decaying, their voices slowly quieting until they become silent and we lose the ability to detect them. The long-period radio transients will keep pulsing their 21-minute signals, patient and unexplained, in the archives of the new radio sky surveys, and somewhere in the southern sky, 390 light-years away, a star will keep burning with elements that should not be there. Promethium decaying towards stability, spectral lines that match nothing in any database. A spectrum that has confounded every investigator who has brought a better instrument to bear on it, and responded to each improvement in measurement precision by revealing a new layer of inexplicability. HD 11065 is not waiting to be explained. It does not require our understanding. It will carry its impossible chemistry into the future, regardless of whether any mind, human or otherwise, ever constructs a theory adequate to contain it. Perhaps that is the point. Science does not offer us endings. It offers us the next question, and the next instrument, and the next moment of noticing, standing at a measuring engine or a telescope or a data terminal, confronted with a number that doesn't line up, a spectrum that doesn't match, a star that sits in a field where no star of its type belongs. The correct response to that moment is not frustration. The correct response is the one that Sandage modelled 70 years ago. Name the thing, describe it honestly, and trust that someone, somewhere eventually, will work out what it means. The stars don't follow the rules. And that, more than anything they could do by following them, is what keeps us looking up.